All right, welcome back, everybody. So we have finally arrived at perhaps one of the most important algorithms that this class is designed to teach you about. We are going to create or show how the discrete Fourier transform works in practice. Now, this one is actually going to be done over 2 videos, so this will be a two-parter. So we're going to be working with the same example, but we're going to do this in 2 different ways. One, we are going to go ahead and work an example by hand, so we see how this method should work in practice. And then in the next video, I'll go ahead and show you how this works in MATLAB and how you might use this to kind of figure out what discrete Fourier transforms look like when you work with them in the computer. So let's go ahead and remind ourselves where we were at the end of our last video. We had just derived this expression for what the discrete Fourier transform looks like. Now, to be very clear about what's happening in this box, we have a function f on the left-hand side, and this function is continuous. This guy just kind of does whatever he wants on the interval from 0 to 2 pi. But the thing on the right-hand side here, this sum of complex exponentials, this is in no way an exact equality. I want to make this abundantly clear. This is not an exact equality unless we are at one of the sample points for the function f. So that's what is being said in here, is that f evaluated at any one of its sample points is going to be exactly what this linear combination of complex exponents or complex exponentials is on the right-hand side, evaluated at that same point. So the coefficients will be given as projections, right? We're going to see them as inner products. We get that from orthogonality. And the thing that we're going to do now is see how to do this by hand. So part 1 is doing this by hand. Part 2 will be doing this in MATLAB. So to get ourselves off on the right foot here, we are going to write out what these linear combinations in on the previous page look like. We're going to write out what they look like in a more compact form, something that is going to be easily translatable into a computer. So we're going to use n-dimensional complex sample vectors. And we're going to write these as omega sub k's, right? So that's not a w, it is an omega. And omega is supposed to represent some sort of frequency type scenario, or something that uses a frequency. And quite frankly, that just means that we're working with the complex exponential with frequency k. And each of the jth entries here, this is a column vector, so the jth row of that column vector is going to be what e to the ikx evaluates to at x sub j. So the sample vector f of our signal is then given as this linear combination of these omega k vectors. Okay, so this is just one way that we're going to go ahead and simplify this expression. So to visualize what's going on here, omega 0, let me keep the definition on the screen. Omega 0 is going to be the frequency 0 complex exponential function. So that is e to the I times 0 times x. In other words, e to the 0. And we all know this. This is going to be 1. Right? So this evaluates to the same thing at each point xj, right? Each sample point xj. So we create a vector of all 1s for omega 0. However, if I go to omega 1, that k now becomes a 1, and I have e to the I times xj. So omega 1 evaluates to e to the pi I, or 2 pi I, times, or e to the 2 pi I over n. And then I have, on the next row, e to the 2 pi I times 2n, and so on, until I get down to the bottom row, where it's e to the 2 pi I times n minus 1 over n. Remember, if I go all the way out to n, I start repeating myself, and I don't want to do that. So technically, is that right? Should I be starting at that one? I should probably be starting at 1, right? E to the 0. Yeah, so this first one, very technically, let me go ahead and extend the column vector here a little bit. This should be e to the 2 pi I times 0 over n. And that should be a 1. Each one of these guys starts with a 1, just to be very, very clear. Right, so each one of these omega sub k vectors has to start with a 1. Okay, so to visualize what these guys are doing exactly, remember Euler's formula is e to the I theta, or for e to the I theta is cosine theta plus I times sine theta. And these components will just be locations on the complex unit circle. So the idea being that if I had n equals 6 here, this will be 2 pi divided by n, which is just the, pi over 3, the 60-degree angle made with the positive real axis. Okay, so that means that these because we're thinking of these locations as angles, right, they're equally spaced along the complex unit circle, right? So it turns out that if I use any one of these guys, I can call this guy a zeta, right? And we'll come back to that notation in a second. But the fact is that these omega vectors, omega 0 through omega n minus 1, form an orthonormal basis in a different inner product space. Remember, I'm trying to define an inner product space for a finite dimensional vector space, and we're going to define our inner product thusly, right? We're working in a Euclidean complex Euclidean space now, but our dot product now looks like the usual complex conjugation, right? So it's our usual L2 norm or L2 metric, L2 inner product, whatever you'd like to call it. But we're also going to scale this guy down by 1 over n. So this one is important. We have to do this, and we'll see it happen in the computer case very, very shortly, like why that is important. It's because we need to make sure we get an orthonormal basis out of this because of the way that the computer figures out the discrete Fourier transform coefficients. But the point is that we are defining a new inner product so that these primitive vectors, as we're going to call them, so that these guys form an orthonormal basis and not just an orthogonal basis of Cn. Right? Because we have an orthonormal basis now, the orthogonal projection with respect to this particular inner product of the sample vector onto the bn's, right, or the beta n vector, or the n-dimensional beta basis, right, the orthonormal basis, just gives us the average of this function here, this f times e to the ikx, over the sample points, right? So if you look at this sum very, very closely, it's just a whole bunch of averages, right? It shouldn't be too surprising here. Now, this is what a lot of discrete computations look like. We have to, or specifically in the Fourier, in Fourier analysis, there's a lot of averaging going on here. We're figuring out different moments in some sense, because we're looking at a whole bunch of different inner products. So that is for our sample vector f, we have our coefficients being exactly just the inner products now. So that addition of the 1 over n makes it so that we don't have to worry about dividing this guy by anything. So in other words, there's no scaling down, up or down, of these inner products, and we can just go about our lives. So note that if I go ahead and define these zetas, right, so in this case, zeta 1, so zeta n, this is going to be what I was doing up here. So in the same notation, in the same spirit of the notation, this should be zeta sub 6. This is the first location after going around from 1 along the unit circle in the counterclockwise direction. This will be the first one of my sample points on the unit circle that I encounter, right? So this is really just the second entry of omega 1, all right? So that's the complex. Oh, excuse me. Sorry about that. That's the second entry of the omega 1 vector. And this is one of what are called the nth roots of unity. And these, we see why they're called roots of unity. It's because they are solutions to the equation z to the n equals 1. Right? So it turns out that there are not one, not two, not three, but n different solutions to this guy, to this equation, and they are all given by different powers of this primitive, this first primitive root of unity. Right? This is a so-called generator of those primitive roots of unity. And there are n of them in general, and these are going to be visualized as kind of taking different powers of this zeta sub 6. So if I multiply zeta sub 6 by itself, I get to this location. Multiply by another zeta sub 6, I get to that one, and so on. So I just keep hopping around until I completely fill up the unit circle, and then I start to repeat myself. So that's what these zetas are doing. These primitive roots of unity are going to be kind of the building blocks for our reconstruction matrices, for our reconstruction vectors. So we can actually see these omega vectors then as just being vectors that have different powers of the roots of unity evaluated for different locations along the unit circle. So we will wind up with quite a few of these guys in general, and they will create a nice compact way for us to reconstruct our functions. And I'll show you in this example. Remember, we're doing something by hand here. It's going to take a little bit of extra effort because we're doing it by hand, but it's going to illustrate what's going on. So we're going to begin with a function f. It's this nice little quartic polynomial. It's got a triple root at 0, and it's got another linear root at 2 pi. But the point is that we know what the entire function f looks like on the interval from 0 to 2 pi. And we would like to sample this guy at 4 different locations. And we're going to evenly space them as per our setup. So we'll space them out at 1, 2, 3, 4 points. And you say, but wait, what about this guy? There's a 5th point. And I will tell you that, yeah, we're going to go ahead and assume this guy is periodic. So point 1 and point 5 start and end at the same location. So we really don't need this 5th point at the far right, so we're going to ignore it. Right? We're just going to completely ignore that 5th location. But we will note that it is there, and it will, as a byproduct of the fact that we're dealing with trig functions, right, periodic functions, that this will actually link up, and we will hit this 5th point as part of our approximation as well. So, using 4 points, we wind up with an exact reproduction of the function f on the sample points 0, pi over 2, pi, and 3 pi over 2. Right? So if we want to create our approximation with these e to the ikx vectors, or e to the ikx functions specifically, then we're going to have to sample at these 4 points. And when we do, we wind up with this sample vector. Right, and I scaled it for our convenience. You can actually plug these in very quickly. All we're doing is using these 4 points in that function upstairs. Right, so first row is a 0. Second row, I'm plugging in pi over 2 into this function. So it's what? Pi over 2 cubed times 3 pi over 2. So there's a 3 pi to the 4th over 16, and so on. Right, so that's all I'm doing to get that f vector. Right? And for our primitive vectors, the primitive roots of unity, if I look on my unit circle, the primitive roots of unity, if I space them out evenly in 4 different locations, I get 1, I, minus 1, and minus I as my 4 different complex number locations, which means that this right here is zeta sub 4. Right, and I can construct my primitive vector, my primitive omega vectors, omega 1 or 0 through omega 3, by just putting the correct powers of zeta 4 in these vectors. And when I do, I wind up with Let me kill that off and move down. When I do, I wind up with these four representations. So remember, omega 1 is always ones, or omega 0 is always ones. Omega 1 just says start at 1 and then work your way around the unit circle. So I get the 1, the I, the -1, and the -I that I just erased upstairs. And then I'm going to go ahead and say, let's go to omega 2. Now, omega 2 says start here, or start at 1, and skip by 2's now. And I'm going to wind up effectively repeating myself if I do that. So I wind up with this vector here for omega 2. Omega 3, on the other hand, says start at 1, but then skip by 3's. So it goes here, and then there, and then back. So I wind up starting at 1, going 270 degrees around until I hit -I. Sorry, I think I missed my... Yeah, so I should have a going to -1 in there. Back up to the top, and then back over. There we go. So I'm just skipping around the roots of unity by 3's for omega 3. Right? I don't skip at all for omega 0. I skip by 1 for omega 1, 2 for omega 2, skip by 3 for omega 3. And if I had more vectors, then that's exactly what's going on. I'm just skipping by the appropriate number of roots of unity. So now that I've got my formulas from the previous page all squared away, right? This guy right here is going to tell me exactly what my coefficients are in my reconstruction formula, or in my reconstruction of the function. So this will just be the inner product of my sample vector with each one of these omega vectors as well, or as one of these omega vectors. So the first one, C0, this is exactly F inner product, so the F vector, sample vector, inner product omega 0. Second one will be the inner product against omega 1. So C2 would be F inner product against omega 2, and so on. And you can compute these by hand. I have it all there in the algebra if you want to pause the video and verify the computations. But I have 4 different coefficients here, C0 through C3, and I'll point out that because I'm dealing with a real function f, that there's a fair bit of symmetry going on across the real axis here. So C1 and C3 are actually conjugates, complex conjugates of one another. Kind of an interesting point of fact here when you use real functions, that you have to kill off all of the imaginary components of this, this complex reconstruction up here, this complex reconstruction vector. So the way that works out is we just kill off conjugacies across the real axis. And it actually winds up being just this simple, that the F sample vector is going to be, and I should be very careful, F sample vector, not F conjugate, is going to be this reconstruction. And I do have a little bit of a plot here to show you what's going on, that you want to pay attention to the purple curve here and the blue curve. So notice that the sample points, 0, pi over 2, pi, 3 pi over 2, and then 2 pi for redundancy, are labeled here across the positive x-axis. But I also have this, this blue curve that's telling me where I've sampled the function. And notice what intersects, right? This purple curve here is intersecting the blue curve on those locations exactly. And notice all the orange curves here, these all hit 0, right? So they all kind of go away at the sample points. But the purple curve agrees with the blue curve at all of my sample points. And that's what I want to take, you to take home here, is that the way that we're dealing with this is by kind of using these e to the ikx functions as interpolators. Right, so they are filling in the space in between sample points, and they happen to equal the sample, what the function evaluates to on the sample points at the sample points. And that's the only time that they really agree necessarily. But do be aware that multiple functions can represent the same signal. So I have a very low frequency term here, this e to the minus ix, and I have an e to the 7ix as well, and I've sampled these functions at 8 equally spaced points between 0 and, I'll mark it here, 2 pi. But notice that these sample vectors, if I sample them at these 8 equally spaced sample points, will actually agree with each other. So the point is that there are many different ways for us to create the same signal with these complex exponential functions. And you want to be very careful with that because this is called aliasing. And aliasing is what gives you a fair bit of strobe of phenomena. And you'll see this to a large extent in when you try to record things that are usually oscillating. So maybe if you're trying to record a fidget spinner, or you're trying to record a strobe light, or you see the weird phenomenon with water seemingly trickling out of a bucket and then freezing midair, or just kind of stopping midair, not necessarily freezing, but seemingly stopping. This is because you're aliasing at the correct frequency. Like you're trying to make it look like things are not moving, or they are sampled at the same spots and they produce the same outputs, but the frequencies are offset at perfect intervals so that they create the same exact signal. So do be aware that this can occur and that there are lots of different ways to sample your functions, especially in a symmetric sense around x equal, or the frequency is around 0. This is also the reason why we have a function called FFT shift in MATLAB. It reduces that aliasing problem, or it centers everything around a common 0 frequency. All right, and this is where I'm going to go ahead and stop the video for the hand, for part 1, for the hand example done by hand.